Across the infinite expanse of the universe, where time seems to stretch and warp, lies one of nature's most extraordinary creations, the neutron star. Born from the explosive death of a massive star, these dense remnants are more than mere cosmic curiosities. They are fundamental to our quest to understand the very building blocks of matter. What profound secrets do these compact giants hold? And how do they push the limits of our scientific understanding? The life cycle of a massive star is a remarkable odyssey, marked by a delicate balance of forces. Nuclear fusion in the core fights against gravitational collapse. This fusion produces energy that creates outward pressure, allowing the star to shine for millions, even billions of years. However, when the nuclear fuel is exhausted, this equilibrium collapses. The core implodes under the weight of gravity, triggering a supernova explosion, a cataclysmic event that can outshine entire galaxies for a fleeting moment. What remains is a core so dense that it transforms into a neutron star, where the laws of physics bend in extraordinary ways. Neutron stars are among the densest objects in the cosmos, with diameters of only about 10 kilometers while harboring 1.4 to 3 solar masses. Imagine holding a single sugar cube of neutron star material. Its weight would be comparable to that of an entire mountain. This mind-boggling density arises from a process where electrons and protons merge to form neutrons, creating a celestial body composed almost entirely of neutrons. The environment within these stars is so extreme that it challenges our understanding of matter, revealing secrets hidden deep within the fabric of the universe. To grasp the complexities of neutron stars, we must explore their internal structure. The outer crust consists of a lattice of heavy nuclei, interspersed with a sea of neutrons, while deeper layers transition into a superfluid state, a phase where neutrons can flow without viscosity. This superfluidity allows for fascinating phenomena, such as the possibility of neutron pairing, where neutrons form pairs that can condense into a superfluid state. As we delve even deeper, theorists suggest the core may contain deconfined quark matter, a state of matter where quarks, the fundamental constituents of protons and neutrons, are free from their usual confinement. This exotic state of matter could shed light on the fundamental forces governing our universe, pushing the boundaries of particle physics. The gravitational forces at play on the surface of a neutron star are monumental, approximately 2 billion times stronger than Earth's gravity. Such extreme gravitational fields warp space-time, bending light and affecting time itself. This distortion allows scientists to observe phenomena that align with Einstein's theory of general relativity, enabling tests of the fabric of space-time under extreme conditions. In tandem, neutron stars possess incredibly strong magnetic fields, often reaching up to 1 trillion times stronger than Earth's. These magnetic fields can accelerate charged particles to nearly the speed of light, resulting in the emission of intense radiation across the electromagnetic spectrum. The interplay between gravity and magnetism in neutron stars creates a dynamic environment, making them ideal candidates for studying fundamental physics. Neutron stars have long captivated astronomers and physicists alike. They serve as cosmic laboratories where we can test the limits of our understanding of matter, energy, and the fundamental forces of nature. The study of neutron stars not only enhances our comprehension of stellar evolution, but also informs our understanding of the universe's fate. Historically, the first neutron star to be discovered was the pulsar PSR B 1919+21, detected in 1967 by Jocelyn Bell Burnell and Anthony Hewish. This groundbreaking discovery opened the door to a new realm of astrophysics, leading to the realization that neutron stars emit regular pulses of radiation, akin to a cosmic lighthouse. This discovery revolutionized our understanding of stellar remnants and paved the way for further exploration of neutron star properties. Pulsars, a type of rotating neutron star, emit beams of electromagnetic radiation from their magnetic poles. As the star spins, These beams sweep across space, producing rhythmic pulses detectable from Earth. This lighthouse effect allows astronomers to precisely measure the star's rotation and gain insights into its structure. Through pulsar observations, scientists have not only confirmed aspects of general relativity, but also developed tests for theories beyond the standard model of particle physics. The study of millisecond pulsars, those with rotation periods in the milliseconds range, provides a unique opportunity to probe the nature of gravity and fundamental interactions at extreme densities. The collision of neutron stars is one of the most profound cosmic events, producing gravitational waves that ripple through space-time. When two neutron stars spiral towards each other and eventually merge, they generate an enormous burst of energy, emitting gravitational waves detectable by observatories like LIGO and Virgo. The groundbreaking detection of gravitational waves from a neutron star merger in 2017 marked a significant milestone in astrophysics. This event, dubbed GW170817, was the first to be observed in both gravitational waves and electromagnetic signals, leading to a wealth of information about the properties of neutron stars and their role in the synthesis of heavy elements like gold and platinum. Such cosmic collisions are not merely scientific curiosities. They play a crucial role in the universe's chemical evolution. When neutron stars merge, they eject material rich in heavy elements, contributing to the cosmic inventory of elements essential for life. The synthesis of these elements during such cataclysmic events challenges our understanding of nucleosynthesis, prompting astronomers to rethink the origins of elements found on Earth and throughout the universe. The study of neutron stars extends far beyond theoretical physics. It has profound implications for various fields, including nuclear energy, materials science, and even astrophysical technologies. Insights gained from understanding matter under extreme conditions may lead to innovations in energy production and storage, enhancing our ability to harness power sustainably. Collaborative research among astrophysicists, nuclear physicists, and material scientists is essential to unravel the complexities of neutron stars. Experimental facilities and high-energy particle colliders seek to recreate the conditions found within these stars, allowing researchers to study nuclear matter under unprecedented pressures and temperatures. By testing theories and models against real-world observations, scientists can refine our understanding of the universe. As we gaze towards the future, the potential for new discoveries related to neutron stars is immense. Upcoming missions, such as the European Space Agency's LISA Laser Interferometer Space Antenna and NASA's Neutron Star Interior Composition Explorer, NICER, promise to offer unprecedented observational capabilities. These missions aim to gather detailed data on neutron stars' structure and behavior. Illuminating the mystery surrounding these extraordinary objects. In the grand tapestry of the cosmos, neutron stars serve as extraordinary symbols of the complexities of matter and the forces that govern our universe.